All right, so I have started recording. So tell me, what did you see in class? You said you saw series circuits and parallel circuits. What are they? What is a series circuit? Somebody? What do we call a circuit that's in series? Nobody has any idea? What about one that's in parallel? Yes, they have the same resistance, I believe. Do they have the same resistance? What's a resistance? What's a resistor first? You've seen resistors. What are the components of circuits? Of course, you must have wires. And what else do you need in a circuit? Electricity and battery. So the electricity comes from the battery. Voltage, charge. Yeah, that's true. What is charge? I mean, a battery, everybody knows what a battery is. I'm not going to ask you that question. Except that you will see in chemistry how a battery operates, if you haven't seen it already, in general chemistry, when you study the electrochemical cell. They were discovered about 200 years ago. Batteries, 200, yeah, about 200 to 250 years ago. So it provides the electricity, of course. But what is electricity? Somebody help. What is electricity? By definition, we use it every day. But what is it? Flow of electrons. Yes, the flow of electrons. And electrons are negatively charged, right? So they flow through the circuit, through the wires, and they have energy, don't they? They have energy because they have speed. Okay, so they have speed, and they give that energy to us. Okay, and that's how we are able to operate our appliances and our electronic devices. It's because those electrons lose their energy. Okay, right. Now, of course, the electricity is not provided only by the battery. I mean, that's one way. We call that a direct current, DC current. And what's the other way of supplying electricity? Anybody knows? So we have a direct current used when we use batteries, but your homes do not use batteries. Yes, alternating currents. Okay, alternating currents or AC currents. That's a second way. Like in your homes, in the buildings where you work, it's AC current that's being used. Okay? It's not direct current. Now, so you said charges flow through the circuit, charges of electrons, and there are other components. What are the other components? So we have wires, we have batteries. What are the other components in circuits? Resistors. Good. What is a resistor? Or can you give an example of a resistor? Like your radio, that's a resistor. Or your television set, okay? Whatever is connected to the circuit, a light bulb, okay? Light bulbs, right? Whatever is connected to the circuit, that's going to resist the flow of electricity. That's why we call it a resistor, because it resists, okay? It resists the flow of the charges of the electrons, okay? Yes, it slows them down, basically. It slows them down, okay? And therefore, that's why we call it a resistor, right? And resistors are characterized by a quantity called a resistance, okay? Whose units are ohms. SI units are ohms, okay? So they tell you, the resistance tells you the ability of that resistor to resist the flow of electrons. So okay, I think that's all we will need today. I mean, we will need also instruments to measure the amount of current in a circuit. And to do that, we use, does anybody know what we use to measure the amount of current in a circuit? What are the units of current, by the way? We've talked about the unit. Ampere. Yes, ampere. Somebody's name. Okay. French scientist, French physicist. Voltmeter. That's a voltmeter. That's an instrument that we use to measure the voltage of the voltage in the circuit. Somebody asked, the higher the voltage, the higher the resistance. Is that true that the higher the resistance is, the lower the current flow? So yes, that's true. That's true, because you can tell it because of Ohm's law. Okay, you've seen Ohm's law today. Have you seen Ohm's law? V equals IR. Yes, V equals IR. So if you solve for the resistance, you see that R equals V over I. R equals V over I. Resistance is inversely proportional to the current. So for the same battery, for the same voltage, if you have higher of one, you have lower of the other. So they are inversely proportional. If the resistance increases, then the current decreases. And as a matter of fact, this is the topic of today's lab. Okay, we're going to study Ohm's law. Increase I, decrease R. That's correct. Increase I, decrease R. Or the other way around. Okay. So that's called Ohm's law. Okay. Iman Kicha, you are asking about attendance. Iman, can you remind me at the end of class, because now I'm recording these the lab. So remind me at the end of class. Now let's talk about. Let me share my screen with you. Okay. So So click and drag the circuit components from sides of simulation screen to get them into work area. So we're going to start with a series circuit. Okay, a series circuit. So let's do that. All right. So we have wires. Take a wire, drag it, click on it and drag it. I'm gonna need a battery, of course. I'm gonna put it here. Maybe need another wire. Connect it here. Move this around a bit. Connect this to the battery. Then the battery a bit. Just make this look nice. Maybe I should move this inside. Wire. And then, of course, I'll need a series circuit. So, some wires. Maybe a switch. Okay. And another wire. This long. And I will need the resistor. The last wire. Okay, and then I close the circuit by clicking on the switch. And the current flows in the circuit. Okay. Why do we need resistors? Because resistors, well, let me see that. Yeah. So why do we need resistors? Well, we need resistors because a circuit without resistors is useless. It would work. Okay, let me remove the resistor. It would still work. See, it works. But it's the electrons flow. But this is an idealized circuit where the wires themselves do not have a resistance, but as a matter of fact, wires themselves have a resistance to current. Okay, so that's why here in this ideal case, the resistance of the wires is 0, but there are no wires that have a resistance of 0. Okay. The only thing that I know of that has a resistance of 0 is what's called a superconductor. Otherwise, all wires have a resistance. So now your question was, why do we need resistors? Because a circuit without resistors is useless. We need resistors because, as we said before, we need to connect our devices to the circuit. Okay. You need to connect your devices, your lamp, your computer, and all of that. And all of that has a resistance, the flow of current. So let me see the other questions.
Professor?
Yeah.
Can we say that like the resistor like controls the passage of the current flow in the circuit?
The resistor controls, it's not controlling it. It's that's what we need. We need I mean, it does of course have an effect on the current through Ohm's law. It does have an effect through Ohm's law because V equals IR, right? If for a constant V, if the resistance changes, of course the current is going to change, like we agreed before. But that's not the main reason why we put a resistor in a current. We put it because it's useful. Because it's useful for us. Okay, like a light bulb. Okay. Let me see. Let me see our messages. Yes. So somebody said, yeah, it's on fire. I explained why it's on fire, right? Because in this ideal situation, the resistance of the wires is zero, and in reality, it's not zero. Okay. So if you see that, if the resistance is zero, okay, then the current is in infinite, an infinite amount of current. So at the same time, I'm reading your messages. All right. So, what else do we need? We need an ammeter. An ammeter must also always be connected to the in series. Okay, so let me remove this. Connect an ammeter. Yeah. And then a wire. All right. Now the ammeter tells us that the amount of current is 0.9 amperes. Okay. And volt, you see, if you click on the battery, you can change the voltage. Okay, increase it or decrease it. Okay, or use this small bar. Okay, let me make the voltage 9 volts. Okay, so what else do we need? We need a voltmeter. Here is the voltmeter. Okay, and with it we can measure the voltage. Let's measure the voltage across the battery. We said it would be 9. Okay, minus 9. Okay, or if you switch the polarity, you should get 9. 9. By the way, here you see that the electrons are flowing in a counterclockwise direction, right? Which is the right direction of the flow of the charges. I mean, yeah, the right direction is the direction of the flow of the electrons. However, electricity was studied in really in a serious way, in a scientific way, starting in the late 1700s and early 1800s, early 1800s. But the electron was discovered. Anybody knows when the electron was discovered? Any idea? Towards the end of the 1800s. Okay, I believe 1897. So, so these phenomena were studied, and people didn't know what was causing electricity. Okay, what was the source of electricity? So they thought that it was positive charges that were flowing through the circuits, and it wasn't negative charges. They didn't know about electrons, and so with positive charges, they would flow in a direction which is opposite that of the electrons. So if the electrons are flowing counterclockwise, the positive charges would flow clockwise. We call that conventional current. Okay, and also the other way around. If the electrons are flowing clockwise, then the conventional direction of the current would be counterclockwise. So if I click on conventional, you see that the current is flowing in the opposite direction. So somebody is 1897, right? That's when, right? 1897. So you see, and the voltage changes also. Well, the voltage is the that. So now we are. So what do we do next? Oh, I can measure the voltage. Notice that the voltage. So here we are saying. Okay, so we are saying here that the voltage from this end of the battery to this end of the battery, the electrons are gaining energy. You see that? But then from, okay, let me move this, from here to here, okay, you see that the voltage is the same as potential difference. Okay, the potential difference is 0 because we are assuming the wires have no resistance to current. So the electrons are not losing their energy when they are flowing through these wires, okay? Which is not realistic because, as I said earlier, in reality, the electrons must lose energy. The wires also have a certain amount of resistance. Now, as the electrons go through the resistor, do you expect the voltage to be 0 also, or do you expect the voltage to change? If I put this here, what do you think is going to happen?
It's going to change.
It will change, right? Because the electrons will have to lose energy. Okay, they will have to lose energy, and you see minus sign because the energy decreases. Okay, and elsewhere in the circuit, because we are assuming the wires to have no resistance, then the voltage should be 0. Okay, it's 0. Everywhere else it should be 0. Can you see that? No voltage. Okay, because we are assuming the wires to have no resistance, which is absolutely not realistic at all. Okay. Or we can also select the values. We are told what the voltage is and everything else. So record on the second page, record in table 1 values for current in circuit as shown on ammeter and voltage across resistor as shown on voltmeter. Okay, so to measure the voltage across the resistor, so we go here, just like we did before, and here is 9, okay, and the current is 0.9. And so we have to change so we keep the voltage constant, and we change the resistance. To change the resistance, click on the resistor and change it. Okay, increase it, and you see that the current changes. Okay, so let me increase it. So at 11, I have 0.8. At 31, I have 0.29. You see that it goes down. Okay, when the resistance goes up, the current goes down. Let me increase it again. 79, and the current goes down. Let me decrease the resistance. Okay. Okay, let me start. No resistance. You see how the electrons are flowing really fast? I mean, here it's the conventional current. So maybe let me go back to electrons. Okay, conventional current is also fine. Okay, but the charges are flowing very fast. But as I increase the resistance, they flow more slowly. Increase more, they flow still more slowly. That makes sense, right? Because less current. Okay. Current, by definition, is the amount of charge that crosses per unit time. Okay, so here we are showing it with the speed of the arrows, but by definition is the amount of charge that flows per unit time. All right, so that takes care of this part. So we need So did you observe that as you increased the value of the resistance in your circuit, your recorded current value was changing? Did your circuit current increase or decrease in value as you increase circuit resistance? So we've answered that question. Okay. Now you need to plot a graph of resistance on your y-axis versus current I on your x-axis. You know how to do that using Excel. We've done it before. Okay. But now, when you add a trend line, like you did in your, I think, first lab, you remember that the relationship between the variables in our first lab was linear. We had a straight line. But this time, because resistance and current are inversely proportional, the relationship will not be linear. Okay? It's going to be like y equals 1. Somebody's intervening. Exponential, yes, exponential, but no, not exponential. It's exponential is not the right word for it. It's a power function. And what we call an exponential function is when the unknown is the exponent. Okay. But for a power function, the unknown or the variable is the base. Okay, is the base, and the exponent is known. And the exponent for us is going to be -1. Okay, because 1 over I is the same as I to the -1. Okay, so when you add a trend line in Excel, do not select linear like we did before. Select power. Okay, power, and make the exponent or the power minus 1, negative 1. And that takes care of the first part of this lab. So that's pretty straightforward, unless there are any questions. Are there any questions, or we can start the second part of the lab? No questions? All right, so the second part, we need to set up a series circuit.
Didier, I actually have a question.
Yeah.
So on the lab, it says that we have to do 7 to 8 data points. However, on the table, it shows only 6. So do we just do 6 or 7 to 8?
Do 8. Do 8.
Thank you.
Okay. Now, so we need 2 resistors this time. Okay, 2 resistors. So I'm gonna remove this. Okay. No, this was fine. Cut this. Or let me open the switch first. Okay. Cut this. And add another resistor. And then connect a wire. Perfect. Now we need the first resistor to be between 2 and 12 ohms. 2 and 12. Number 10 is fine. That's between 2 and 12. And then the other one to have a resistance between 20 and 100 ohms. That's 71. Okay. You can drag circuit components to construct a series circuit. All right. Now what are we supposed to do? Record your battery voltage, record all other data in table 2 below. Okay, so let's close the circuit and current flows. Okay, so you're supposed to the voltage, to record the voltage and the current through the resistor. So that's all. That's all you're supposed to do. Okay. I hope you are all have well, since you are going to practice in a while, then you'll be able to ask questions if you encounter any difficulties. But this is what you're supposed to do here. So the battery voltage is here. Just make it positive. Don't worry about negative here. Okay. Don't worry about the minus sign. All right. Don't worry about the minus sign. So this will be 1.11, and the other one will be 7.89. Okay, so that's the voltage across the second resistor, 7.89. So don't worry about the minus sign. That's not what matters for this lab. Okay.
Professor.
Yeah.
So to measure the voltage of, like, let's say the resistor, you got to put like the 2 wires, like you got to put the resistor in between the 2 wires, right?
That's correct. Yeah, of the voltmeter.
Okay.
Yeah.
Okay.
Yeah, that's how you have to do that. That's correct. Between the black and the orange wires. Yeah, that's correct. So now we need to replace your resistors in series by 2 light bulbs. Okay, you turn on the switch. So we will have the same effect. Not that we have voltage of 7.89 minus. If I replace this, remove. Oh, let me open the. And then replace this with light bulbs. Was it, what was the resistance? Was it 71? Does anybody remember? I think it was 71. You can change the, oh, we can change the resistance here of the bulb? Oh yeah, we can. I think 71, I think. Does anybody remember what resistance we had in the first case? Because you see the light bulbs, they play the role of resistors. They have a resistance too. Okay. And
Professor, don't you gotta connect the first light bulb too?
oh yeah. Oh yeah. It's not connected, is it? It's not connected. Okay, sorry about that. It's not connected properly. I thought it was. So we gotta be blue. No red. Thank you. And we get the same thing, right? The same thing as before. So light bulb is a resistor. So now the question is, observe what happens. Are the light bulbs brightly lit? Well, if I have only one light bulb, okay, let me make this resistor, the resistance 0. If I make this 0, I'm basically, it's the same thing as removing it from the circuit. Okay, so you see that this light bulb shines brightly. Not very clear. Lower this a little bit. You see, it's shining very brightly, isn't it? But then, if I okay, somebody is intervening. Okay. So why is the one on the left lighting up and not the first one? Okay. Well, there's no resistance in the first one. I've effectively removed it by making its resistance 0. I made its resistance 0. When I increase its resistance, you see, it starts lighting up. It starts lighting up. Okay. Let me increase it more. And you see what happens to the other one? Let's make the resistance the same, 10 everywhere, right? What do you say is happening? Are they shining brightly? They are not, right? Because they were shining when there was just one light bulb, it was shining brightly, but now there isn't. Okay, and if I make the resistance higher for the one on the right, you see they don't shine very brightly. Okay, all right. I think that's it for the series circuit. Now, resistors in parallel. Okay. So to be in parallel, so we need to use resistors. So let me remove the light bulbs. Click. And then, trash can. Click trash can. And then, so in parallel, I'm gonna do this. Remove this.
Professor, sorry, can you explain again why like the light bulbs are brightly lit?
Well, it's because they're in series, because they're in series. Okay. The current through the wire for a series circuit must be the same. Okay. So maybe let me include another ammeter to show you. That's a good question. The current here. Let me go back. Another ammeter. And then but the voltage changes. Okay, the current is everywhere the same, but the voltage changes. And then the light bulb. Sorry about this. Cut. Now it's connected well. And now another one. And then the last light bulb. Do you see that the current is everywhere the same? Okay. The current is everywhere the same in the circuit. Okay. But the voltage, okay. Yeah. Okay. All right. The current is everywhere the same, but the voltage, let me extend this a bit so I can measure the voltage. Here is going to be different. The voltage here, I don't know if you can read it, is 1.36 on across the light bulb on the left. It's 1.36. The voltage across, because it's a V equals IR, right? So current is, yeah, here they're rounding, okay? They're rounding, so 10, the resistance is 10 times I, the current 1.4, 0.4, you see you get 1.36, so 1.4, right? Now, Here, let's measure the voltage. You see, it's completely different. It's completely 7.64. Okay, take 0.14, multiply that by 56. You should get something around 7.64. They just rounded. Okay, let me do that. I have a calculator here. So we said 6 times 0.14. Yeah, around that. Okay, around that. It's because they are rounding. The current is being rounded. So that's why. So basically, the voltage is being shared. Okay. If you add up the two, you should find the voltage of the battery. So what did we say? So 7.64. All right, plus 1.36. What is it? Isn't it 9? Okay, let me do that on my calculator. 7.64 plus.
Yeah, it's 9.
Right. It's 9. Okay. Yeah. So a good way of explaining this that will maybe help you understand is with potential energy, because this works just like in the case of gravity. If you have you have potential energy. So if you have a like a ball, for example, and you put it high in the air, it has some potential energy. If you put it higher in the air, it has more potential energy. And as it goes down, it loses its potential energy. Okay? In the same way, the electrons, when they start here at this terminal of the battery, all right, they have a lot of potential energy. And as they cross resistors, they lose their potential energy. Okay, that's the same thing as going down. So they lose their potential energy until they get here at this other terminal of the battery where they have no more potential energy. They have lost all of their potential energy, which is the same as for the ball reaching the ground. Okay, if you want the ball to acquire more as much potential energy as before, you have to lift it up and put it high in the air. That's the same as taking the electrons and taking them from this terminal to the other terminal. Okay, so that's exactly what's happening here. Okay, so the energy that the electrons had when they started from the one terminal of the battery, they lose it as they cross the circuit. But the amount of energy, but that amount of energy has to be shared between the two lamps, between the two light bulbs. Okay, because it has to be shared, then they don't shine brightly. Okay, it's not as if all of the energy was spent on just one light bulb. So that's why. So does that answer your question?
So yeah, I understand it more. So because we're talking about a series circuit, the energy is shared. So because the energy is shared, it's shared unequally to the point where one light bulb will be more brighter than another,
Right.
more brighter than another.
Right.
Okay.
Because the voltage is being shared. Okay.
Yeah.
And through Ohm's law, right? Through Ohm's law, the one that has a higher resistance, okay, because you see that the current is the same everywhere, right? That's why I've included all these ammeters. You see the current is the same, 0.14 everywhere, right? Through Ohm's law, if the resistance is higher, the voltage is higher. And the voltage is potential difference. And potential difference is energy change. Energy change. So the energy. So here you see the one that has a smaller resistance has a smaller potential difference, and the one that has a higher resistance, because V equals IR, you multiply by a bigger R, you multiply I by a bigger R, you get a bigger V, bigger potential difference. Okay, so bigger potential, ignore the minus sign. Bigger potential difference means more energy lost. So the light bulb, this light bulb will shine more brightly as it's acquiring more energy from the electrons as they are losing that energy. All right.
Thank you. I get it. Thank you.
You get it. Okay. For the parallel circuit, it would be the other way around. Okay. The currents will be different, and the voltages will be the same. And that's, as a matter of fact, that's what we are going to do now. Okay. So let's do that. Yeah, remind me to include the ammeters so that you see. Yeah, include the ammeters in your circuits. That then you will understand this better. All right. Let me remove this. Remove. Let me click on it. Remove it. So how do I do this? Cut this. All right. I include a new wire. So what do they say? They say resistors have the same. Construct your resistors in a parallel circuit in your simulation. Record the data for resistors in parallel circuit in table 3 below. Okay, so we need them to be in parallel. Okay. Okay, what's this for? This is not useful. Oh, it was useful. I want to include another ammeter. Oh no.
Excuse me?
Yes?
Can I ask you if mine is correctly in like parallel for part 3, if it's correct, the setup that I have?
Yours?
Yeah.
But I will have to stop sharing. That's the problem.
Oh,
And I wanna do this. I wanna make sure. Yeah, that's the problem. I will have to stop sharing.
I see.
Yeah. The problem is that I wanna include all the ammeters so that we see what the current is everywhere. They're not asking this in the lab, but I wanna do it so that you understand what's going on more clearly. Okay. I should really okay. Good. Okay, nice. Okay. All right, I think this is it. Nice. Okay. Is it clear to everyone that this is this resistor? This is a parallel circuit. Maybe. Oops. Nice. Okay. All right. Is it clear to everyone that these resistors are in parallel? All right. They are, right? Now let me close the circuit. Current flows, and already. Okay, let me change the resistance because it's not supposed to be the same. Here it's the same because the current is the same. It's not the same everywhere, right? Remember that it was the same in the series circuit, but here, in this case, the current is not the same, but it's the same for both resistors because the resistance is the same for both resistors. But let me change the resistance. Let me make this, I don't know, 82, for example. All right? So what do you see? The current changes, right? It's nowhere the same. It's absolutely nowhere the same. The current in the left, the resistor on the left is not the same as the current in the resistor on the right. And it's not the current overall in the circuit. Okay. The current overall in the circuit is 1.01 amperes. Lina, okay, so I have a few, so some people are making comments. Let me see, let me read your comments. So somebody asks, are we using the light bulbs as resistors or use the resistors? Well, there are many parts to to the lab. So sometimes they ask you to use the resistors all by themselves, and sometimes they ask you to use the light bulbs as the resistors. Okay, so you'll have to do both. And then somebody is asking, no, you're following the lab manual. That's all I've done. The only change I've made is that I've included many ammeters. And the reason why I'm doing this is so that you understand what's going on with the current. Okay, how the current is changing through different pieces of the circuit. Okay, and that's why it's taking a little bit of time, because I'm trying to insert all these ammeters in the circuit. Right, so but we are doing exactly the same as in the lab manual.
I have a quick question.
Yeah.
So this setup that you have here on your screen, is that the setup that we would kind of go for where it says part B, resistors in parallel, on the second to last page of the lab manual?
Yeah.
Okay.
No, the second to last. Yeah.
All right. Because you have the two parallel resistors.
Yeah. That's correct.
Right.
That's correct.
Thank you.
Yeah, you just notice that there in the figure, they're not including the ammeters. They're not inserting them in the circuit. But Liana, you are raising your hand. Yes.
But in that last section, there's only one column for the current reading. So how would we do our setup? Where should we put the current reading? Like, because there's only one column and we can't write all three how you have it here.
All three. Well, look, but there are 3 rows. There's one column for the current, but 3 rows. The first row for the first resistor, the second row corresponds to the second resistor, and the third corresponds to the current overall. Do you see that?
Right.
So as a matter of fact, you do need these ammeters everywhere. Or I guess what they're asking you to do is to compute them using Ohm's law. Because if you use Ohm's law, right, V equals IR, right, you have to find the voltage first. We can do that using Ohm's law. Okay, let me see. So the voltage across this resistor, the one on the left, you see the voltage is -9, okay, the same as that of the battery. The voltage across the second one is also -9, the same as the battery. You see, the voltage, as we said earlier, does not change in a parallel circuit. It doesn't change. So to find the current, divide the voltage by the resistance. If you take if you take 0.9, because the voltage is 9, and you divide that by 10, since the resistance is 10, you get the current of 0.9. That's exactly what we got. So you don't need to insert these ammeters in the circuit. You can just use Ohm's law, V equals IR, right? So which means that the current, which is I, is V over R. And in the same way, for the second current, for the current of the through the resistor on the right, take the voltage 9, it's 9, right? That's 9, and divide that by 82. What's 9 divided by 82? 9 divided by 82. I'm doing that on my calculator. And you see you get 0.11. And that's exactly what we have as the current through the resistor on the right. See that? So you do have enough columns and enough rows in the table. Does
Professor?
does that answer your question, Diana?
No, because I was just talking about. I understand now that we should probably use the formula to find A, but I was just asking because you have 3 different current readings, so I didn't know which one coordinated to which.
Oh yeah, you don't need them. If they bother you, don't include them. Don't use them. Okay, just remove them. Just remove them, and just use the formula. Okay, I should do. Yeah.
And just to be clear, the battery voltage would stay the same. It's expected to be the same. That
Same everywhere because it's a parallel circuit. Okay, so now let me see. There are people who have other questions.
I have a question, Professor.
Yeah,
So like in terms of a parallel circuit, right?
yeah,
Regardless, because I know in the series, because the higher the resistance, the higher will be the voltage. But in terms of like a parallel circuit, it doesn't really matter the resistance, the voltage will still remain the same, right?
yeah,
Okay.
yeah. It will always be the same. So let me read your questions. So we have to use resistance from 3 to 5. Well, it says in the instructions file. Okay, what values you have to use. Yeah, it says okay. This question also it says in the instructions. Okay, so I think all right. So what else do you have to do? And then you've seen formulas for computing the equivalent resistance in class, haven't you? All right. If you haven't, you will see them as this week. You have another class this week, a lecture. Somebody's.
Yeah, we do.
You do. Okay, good. So if you haven't seen the formulas for finding the equivalent resistance, you will, right? But they are included in the lab.
Oh, Professor, I have another question.
Yeah.
Regardless of whether it's a parallel circuit or a series circuit, the voltage of the battery will remain the same, right?
Yeah, we're not changing it. We're not changing it because we're using the same battery.
Okay, yeah, just making sure.
The battery does not, its voltage doesn't change.
Oh, I have a question. So you said that on the lab, it's supposed to be from 3 to 5 for resistance, but wouldn't it,
Yes, keep going.
yeah, wouldn't it be okay? Because I did from 10 to 80. Wouldn't it show the same type of slope? If
Well, 3 to 5 is because it said so in the instruction file. It said so on some page, but it said so. It said okay. Let me. I'm not sure I'm gonna find it. It said. Yeah, no, I can't find it. But if you just follow the instructions,
all
just
right.
follow the instructions. I think it said 3 to 5 for one resistor, and then 10, 12 to 80 or to 100 for the other one. I don't remember.
And when we do a 3 to 5, that includes decimal points, correct?
Yeah.
Okay, cool. Thank you.
No. And then somebody. So is it okay for the? We've answered that question. So now, what else? So you said that you have cast this week, so and then also next week, so you will see these formulas. Plus, they are included in the file anyway. So now the last fourth problem: replace your resistors in parallel in your simulation by 2 light bulbs. Turn on the switch and observe the light bulbs. Are they brightly lit? Why? Now, let's think together, right? We said the potential difference, that's what gives energy to the light bulbs, right? But we said the potential difference here is not gonna change. So what do you expect is gonna happen when I remove the light bulbs and I replace them, I remove the resistors and I replace them by light bulbs? Are they going to shine brightly or not? The voltage doesn't change, right?
Yeah, they will shine brightly because the voltage will remain the same for both of them.
That's correct. That's correct. The voltage is the same, therefore the same amount of energy is expended in both each, and therefore the same level of brightness should
The
be
same amount of energy is being shared, so they will have the same amount of brightness.
the same amount of, yeah, the same amount of energy goes through each. Yeah, yeah. If they have the same resistance, yes. Okay. Wait. No. Oh, I've already removed it. Sorry about this. So regardless of the resistance, the same amount of voltage goes through both. It's only the current that changes when you change the resistance, not the voltage. Okay. And therefore, their level of brightness will be the same. And we close the circuit. And you see that both shine very brightly. Okay. Okay. For the same amount of current, they shine brightly. From the same voltage, they shine brightly. Except more brightly than in the first case. So which circuit configuration do you think is widely used in homes, offices, and industrial systems, and why? So which one is used, series circuit or parallel circuit, in homes, offices, buildings, and so on? No idea, and then you have to explain why. No idea. Well, because we want to achieve a high level of brightness, okay, use our energy efficiently, we should use which one, the first or the second, series or parallel? The answer is parallel. Yes, we use a parallel circuits. Okay, but series circuits are also useful in certain applications. Okay. Because think about it. If there is a problem, so if these are in parallel, right? If there is a problem in part of the circuit, okay, some, this is cut, for example. You see, the other part of the circuit, the second part of the circuit, is completely independent of the first one. Okay, so the current keeps flowing. Okay, so there's no problem. If you have several rooms and there's a problem with the wires in one of the rooms, and the circuit is set up in parallel, then there's no problem with the other rooms. Okay, but let's say that you have a Christmas tree, for example. All right, and then oh, maybe that's not a good example. Okay, let me think of another example where I can think of an application, but I know that there are applications where you have many light bulbs, or for example, or many devices connected to the circuit. They don't have to be just light bulbs. And then when one doesn't work, when the current doesn't flow through one, then it doesn't flow through all the others, even if there are 100 of them or 1,000. Okay, and in that case, the circuit is effectively open. There are important applications of that, but it's just that I can't think of one right now. All right, so that's the end of the lab. Are there any questions?
Oh, so Professor, just to reiterate, when we talk about like which like circuit configuration like is used widely, like in is used, right? Just from my understanding, like the parallel ones, right? Because like if one wire, like if there's a malfunction on one wire, then that doesn't affect like the power source of the like others of the like other light bulbs, you know.
Yeah, but yes, that's one of the reasons. But another reason is that we get the same higher efficiency in our use of energy. Well, because you saw that the light bulbs were brighter with the parallel circuit than with the series circuit. Okay, so it's more efficient. It's just more efficient. The light bulbs shine more brightly.
You said it's more efficient.
Yes.
Okay, gotcha. Thank you.
Any other question?
I have a question, but it's more like a personal one, so I'll wait after class.
It's personal. Okay. After class. No other? Also in the chat. When will the recording be posted on YouTube? Probably in an hour or two. Maybe a bit longer. But definitely tonight.
I have a question.
Yes.
For the second table, you know how you were saying you can calculate the currents for the third table? Are they not supposed to be the same for the second table? Because all my values were the same. Is that wrong?
If the resistance is the same, yes, they will be the same, but they will not be equal to the total current.
Okay.
Yeah, but they will be the same. That's true. The total current is the sum of the two. Remember, we had. It's still there. Let me share my screen with you. That's a good question. Let me share my screen with you. So here we have. So let me make it different. Okay. So here we have 0.16 plus 0.90. You see, you get that's 1.06. Okay. The current is the sum of the two. Just like of the two pieces, the current overall in the circuit is the sum of the two currents. Just like the voltage in the series circuit overall is the sum of the voltages across the two pieces, across the two resistors.
So we would record the 1.06 in our table for all three.
No, because they have different currents. You have to record 0.90 for the resistor on the left, 0.16.
Yeah,
for
but
the
that's for the
resistor.
parallel one. I'm talking about for
Yeah.
the non-parallel.
Yeah, for the series one, it will be the same current everywhere.
Okay.
Yeah, exactly. Another question? All right. Since there are no other questions, then I'm going to stop recording. And then